The sizes of cosmic objects are incredible. Sometimes it is hard to believe that barely visible points of light scattered across the night sky can turn out to be giant spheres of incandescent plasma capable of swallowing entire planetary systems. Some of them are distant from Earth by hundreds and thousands of light years, a trifle by cosmic standards. Today, we will set out to the most prominent of these luminaries. Our fantastic journey will begin with the star most important to us, the Sun. Then, we will explore several stars near it. And further, we will venture into the depths of the galaxy to a burning monster hidden among interstellar clouds. The next stage of our path will be the pulsating fire, Betelgeuse, which at any moment could erupt into a deadly supernova. Leaving the dying star behind, we will head toward a true giant capable of swallowing tens of millions of stars like our Sun. Next, the majestic hypergiant Stephenson 2-18, the largest known star in our galaxy, awaits us. And to conclude our journey, we will peek into a stellar nursery, the Orion Nebula. Get ready, we are beginning. The Sun. Primarily, the Sun is a main sequence star approximately 4.6 billion years old. Currently, it belongs to the spectral class G2V, which allows us to consider it a typical yellow dwarf. The surface temperature of the Sun is approximately 5,510 degrees Celsius. However, there are both hotter and cooler regions on it. At the same time, its outer corona is heated to millions of degrees, though its contribution to visible radiation is almost imperceptible. The average diameter of the Sun is approximately 1.4 million kilometers and exceeds the size of our planet by 109 times. Its mass reaches $2 times 10 carat $30 kg, or 333,000 Earth masses, which constitutes 99.9% of the mass of the entire solar system. We are used to considering the Sun a small star, but in reality, it is larger and brighter than 80% of all known luminaries in our galaxy. 92% of the Sun's volume is hydrogen. This gas, heated to incredible temperatures, is the main fuel for the thermonuclear reactions that support the glow of the absolute majority of stars. By fusing, hydrogen nuclei release a vast amount of energy and turn into helium, which gradually accumulates in the star's core. Currently, helium makes up about 7% of the Sun's volume, or 25% of its total mass. Besides helium, stellar matter contains other elements such as carbon, oxygen, nitrogen, and iron, but their share is insignificant. The Sun has a complex structure and consists of several layers, each with its own characteristics. The central part of the luminary is occupied by a massive core, the diameter of which, according to calculations, is about 25% of the star's total size. The core temperature reaches about 14 million Kelvin, and every cubic meter of its matter weighs approximately 150 tons. It is here that the thermonuclear reactions occur, serving as the energy source for the Sun's light. As a result of these processes, about 4.26 million tons of stellar matter are converted into radiation every second. The core is surrounded by the so-called radiative zone, extending to 0.7 solar radii. The density of matter in this region is too high for it to mix freely and carry heat to the upper layers of the star. Therefore, energy is transferred here through the constant absorption and re-emission of stellar plasma particles. The temperature of this zone changes from 7 million Kelvin in the depths to 2 million Kelvin at the outer boundary. According to calculations, a photon of light born in the core can spend between 10,000 and 170,000 years in this zone before reaching the next layer of the star. This next layer is called the convection zone. The matter in it is thinner and more mobile. Therefore, giant vortices constantly arise here, carrying hot plasma from deeper regions upward, while cooled outer masses sink downward. These convection cells remain stable for 10 to 15 minutes, after which they collapse, forming new vortices. The constant movement of matter creates a magnetic field that permeates the entire solar system. Additionally, the Sun is surrounded by an atmosphere consisting of several complex layers. The lowest of them is called the photosphere. This is the region that emits most of the star's visible light. Therefore, when we look at the Sun, this is what we see. The thickness of the photosphere is from 100 to 400 kilometers, and the temperature varies from 6,600 to 4,000 Kelvin. Above lies the thinner chromosphere, about 2,000 kilometers thick. It can be observed from Earth during a total solar eclipse or with special instruments. This is a very hot zone, with temperatures ranging from 4,000 to 20,000 Kelvin. Its outer boundary is covered with spicules, elongated bursts of hot gas 5,000 to 10,000 kilometers high. The outer layer of the Sun's atmosphere is called the corona. It consists of giant prominence flares and ejections, the sizes of which can reach 1,000,000 kilometers. The matter of the corona is extremely rarefied and scorched. Its average temperature is 1 to 2 million Kelvin, with peaks up to 20 million Kelvin. It is into this zone that the Parker Solar Probe periodically plunges, going deeper into the solar abyss each time. If we calculate the energy flux emitted by the photosphere, it turns out to be insufficient to heat the chromosphere and corona to such high temperatures. This means that certain unknown processes are occurring on the Sun that additionally heat the upper layers of the atmosphere. There are several scientific hypotheses attempting to explain this temperature paradox. According to one, the chromosphere and corona receive additional energy through wave dissipation. Another assumption is based on the effect of accelerating charged particles in the star's superpowerful magnetic field. To bring clarity to this issue, the Parker Research Probe was created. This automated research station is part of a NASA project called the Parker Solar Probe, launched in 2009. After 9 long years, on August 12, 2018, Parker left Earth forever and headed toward the Sun to fulfill its mission. However, before that, it had to perform a series of maneuvers to enter the planned orbit. Using Venus's gravity, Parker gradually changed its trajectory, step by step approaching the burning star at the center of our system. It was equipped with a special heat-reflective shield, and all the equipment was manufactured taking into account extreme operating conditions. Parker's calculated orbit passes in close proximity to the Sun, but the craft remains there for a relatively short time before moving away, allowing it to release accumulated heat into space. The main task of the craft is to determine the structure and dynamics of magnetic fields in the immediate vicinity of the Sun. Additionally, Parker is to measure the energy flux coming from the luminary, study the solar wind, and capture charged particles. A side result of the mission was images of Venus and Comet C/2020 F3 obtained during the approach to the Sun. To successfully perform its tasks, the probe is equipped with a wide range of measuring instruments and cameras. However, its work is hindered by a strong flux of ionizing radiation. Furthermore, the Sun creates powerful radio noise around itself, which complicates data transmission to Earth. Despite this, Parker continues its flight, shortening the distance to the luminary with each orbital revolution. At the end of February 2022, it was to pass through the solar corona once again to collect a new portion of data, and by 2024, the distance between the craft and the Sun's surface had shrunk to a record 6.5 million kilometers. Calculations show that at perihelion, the probe's speed already reaches 163 kilometers per second, and over time it will grow to 200 kilometers per second. This will make it the fastest spacecraft created by humanity. The Parker Solar Probe successfully completed its close approach to the Sun, reaching a record distance of approximately 6,100,000 kilometers from its surface. This approach allowed the station to collect valuable scientific data about the Sun's corona and the solar wind. After this, data collection continued, and on January 1, 2025, new data was received from the station. The Parker Solar Probe mission continues, and it continues to send data that helps study the mechanisms that heat the solar corona, the origin of the solar wind, and the acceleration of energetic particles. Unfortunately, its lifespan will not be very long. After reaching the minimum distance to the Sun, Parker will perform several orbits around it, which will take about a year. During this entire time, it will gradually lose speed, and the onboard instruments will be subjected to extreme temperatures and powerful radiation. Eventually, the probe will fail, and the craft itself will plunge into the scorched depths of the Sun, where it will be completely destroyed by the ocean of burning plasma. However, before that happens, Parker will transmit a huge array of valuable data to Earth, allowing humanity to take another step in the study of space. Thus, its flight will not be in vain. The depths of any star are heated to incredibly high temperatures, and this is no surprise, as only under such conditions is thermonuclear fusion possible, the main energy source for all stars. The fusion of two hydrogen atoms leads to the formation of a helium atom, the emission of an electron and several neutrinos, as well as the release of a vast amount of energy. However, hydrogen-helium fusion is not the only process heating stars. At even higher temperatures, lithium, carbon, or oxygen can participate in reactions. In this case, nuclei of heavier elements such as sulfur, magnesium, or phosphorus are formed. They have a higher charge and repel each other more strongly. So much greater energy is needed to overcome this resistance. When a main sequence star burns most of its hydrogen supply, it begins to expand and cool, turning into a red giant. Its burning is sustained for a time by thermonuclear reactions converting helium into carbon and oxygen, but the smaller the mass of the luminary, the shorter this period is. Eventually, the star becomes unstable and sheds its outer shells, turning into a nova, and a white dwarf remains in its place. A white dwarf no longer has fuel for a thermonuclear reaction and, without an energy source, is forced to cool gradually. However, if the luminary's mass exceeds a certain limit, heavy thermonuclear fusion can become the main energy source even after all the hydrogen is exhausted. Such celestial bodies are called Wolf-Rayet stars. This class of cosmic objects was discovered back in 1867 by French astronomers Charles Wolf and Georges Rayet. Scientists' attention was drawn to the abnormally bright emission lines of heavy elements in the spectrum. The nature of their radiation was explained much later. Usually, stars of this class are massive and hydrogen-poor luminaries at the final stage of evolution. Wolf-Rayet stars are very rare in our galaxy. Only a few hundred such luminaries are known. It is believed that in the Milky Way, there are no more than 2,000 such objects. Wolf-Rayet stars are divided into three main sequences according to the brightest element in their spectrum: nitrogen, carbon, and oxygen. Each of these, in turn, has several types. To the oxygen sequence belongs the hottest known star in the explored universe, object WR102. This star was discovered back in 1971. Initially, it was considered an optical counterpart to the X-ray source GX3+1. Further observations showed that these are completely different objects. According to spectral analysis data, the discovered luminary was distinguished by extremely bright oxygen lines in the emission spectrum, and in 1982, WR102, along with 4 other bright stars, became the prototype for creating a new class. Spectrum studies show that the surface temperature of WR102 exceeds 210,000 Kelvin. Thus, this star is approximately 36 times hotter than the Sun. Its luminosity is simply incredible, 380,000 times higher than solar. The distance to WR102 is about 10,000 light-years. The object is located in a patch of sky belonging to the constellation Sagittarius, but it is impossible to see it with the naked eye despite its huge luminosity because it is too far away. Its composition contains a lot of oxygen and almost no hydrogen. The fusion of heavy nuclei of elements such as neon, carbon, and oxygen is the main source of energy. To date, only 9 such objects have been discovered, 4 of which are in the Milky Way and 5 in other galaxies. The rarity of the oxygen sequence is explained by 2 factors. First, there are very few Wolf-Rayet stars in general, as only luminaries with a mass of at least 40 solar masses become such. Second, this class is the final stage of evolution for stars of this type. This stage lasts from 1 to 10,000 years, a blink of an eye by cosmic standards. WR102 is a small but dense star. Its radius is only 58% of the Sun's radius, and its mass is determined to be within 15 to 18 solar masses. It is assumed that at the time of formation, it had a mass of 40 to 60 solar masses. However, High temperatures and turbulent reactions in the star's depths cause an incredibly powerful stellar wind, the particle speed of which exceeds 5,000 kilometers per second. Over a period of several months, thanks to the stellar wind, WR102 loses an amount of matter equal to the mass of Earth. At such intensity of particle radiation, in 10,000 years, the star will lose as much matter as the Sun weighs. WR102 has no planets, but is surrounded by a rarefied gas shell. Powerful ultraviolet radiation and a strong stellar wind compress and ionize it, forming a complex system of prominences and arcs around the luminary. According to one theory, the gas nebula around WR102 may be the remains of the star's hydrogen outer shell, an assumption based on the flux of particles the star ejects. WR102 is not the only incredibly hot place in the universe. For example, stars WR12, WR30A, and the central star of the Bug Nebula NGC 6302 have approximately the same surface temperature. Some white dwarfs can also reach similar temperatures, but none of them compare to neutron stars. At the moment of their birth, the temperature can reach 100 billion Kelvin. Active neutrino radiation cooled June 2021. Data from ground-based telescopes confirmed this hunch. Astronomers continue to observe the object while astrophysicists model the processes in its depths. Before trying to understand what happened, it's worth understanding what Betelgeuse is. This object belongs to the class of red supergiant stars and, according to the modern theory of stellar evolution, is at the final stage of its life cycle. Its luminosity and radius are constantly changing, and its outer shells are extremely unstable. Periodically, the luminary ejects millions of tons of scorched gas into space, forming giant prominences. As they cool, they replenish the gas nebula surrounding Betelgeuse. Its mass is about 17 solar masses, and its diameter, by rough estimates, lies within 700 to 880 solar diameters. If one were to mentally place Betelgeuse at the center of the solar system, it would swallow all the planets up to Mars inclusive, as well as a significant portion of the asteroid belt. At the same time, it should be noted that the star does not have a clearly defined edge, as its outer shells are very rarefied. Furthermore, the object is surrounded by a giant gas nebula consisting of cooled prominences and particles of stellar matter. The density of matter at the conventional boundaries of the star only slightly exceeds the density of the nebula itself. Betelgeuse is an extremely bright star. Its minimum luminosity exceeds the Sun's by 90,000 times, and at the peak of its brilliance, it emits 150,000 times more light energy than the Sun. Meanwhile, its surface temperature is low, from 3,400 to 3,800 Kelvin, which corresponds to the red part of the spectrum. In the unstable outer shells of the star, unpredictable processes constantly occur that change its luminosity in complex ways. The main pulsation period is approximately 420 days. At the same time, less pronounced cycles of both greater and lesser duration can be distinguished. Furthermore, unpredictable flashes and fades of light are observed from time to time. Due to this instability, calculating the exact distance to the object is extremely difficult. According to measurements conducted by the Gaia satellite in 2020, the distance from the Sun to Betelgeuse is between 500 and 650 light-years. According to modern ideas about stellar evolution, Betelgeuse formed approximately 8.5 million years ago, having an initial mass of about 20 solar masses. Its life path began in a giant cloud of interstellar gas, which was gradually compressed and heated by gravitational forces. Thus, the protostar mother of Betelgeuse was born. At the moment when the temperature and pressure in its depths reached a certain threshold, a chain reaction of converting hydrogen into helium began, and a new cosmic object instantly shone. This begins the longest period in the life of any star, the main sequence stage. During this time, the main source of energy is the fusion of hydrogen atomic nuclei to form helium, and the more massive the star, the faster this process occurs. The lifespan of massive stars like Betelgeuse is millions of years, whereas red dwarfs shine for billions of years. In any case, Luminaries spend about 90% of their lives on the main sequence. Gradually, helium accumulates and sinks to the center of the object, where it forms a helium core. The star's further fate depends almost entirely on its mass. For example, luminaries whose mass does not exceed 20% of the Sun's end their life path with a faint flare, unlike more massive stars. By gradually processing almost all their hydrogen, they slowly turn into blue dwarfs, hot and relatively small astronomical objects. However, the minimum time required for such a transformation is about 1 trillion years, which is 72 times the estimated age of the universe, so there is almost no chance of discovering a blue dwarf at present. After exhausting hydrogen supplies, thermonuclear reactions in them stop, and the object becomes a white dwarf, 99% composed of helium. It awaits trillions of years of slow fading and cooling until a barely warm and almost invisible black dwarf remains in the star's place. If the object's mass lies within 0.2 to 8 solar masses, its evolution is much more complex. The helium formed by thermonuclear burning replenishes the luminary's core, and gravitational forces compress and heat it even more. At a certain point, a fusion reaction of helium nuclei to form carbon is triggered, the star begins to expand, its radius grows, and the temperature of the outer layers decreases. In this case, the object turns into a red giant or subgiant. Relatively light luminaries, whose mass does not exceed 50% of the Sun's, are unable to maintain conditions for a steady helium reaction. In them, such transformations occur only occasionally. In more massive objects, reactions in the stellar core can continue, forming carbon, oxygen, and other heavier elements up to nickel and iron. Eventually, the luminaries shed their outer shells, leaving behind a white dwarf surrounded by a planetary nebula. If the initial star's mass did not exceed half a solar mass, it will mostly consist of helium with a slight admixture of heavier elements. Otherwise, the main mass of the white dwarf will be oxygen and carbon, and in the case of a sufficiently massive parent star, neon, magnesium, and even iron may be found in its composition. The evolution of massive objects has its peculiarities. As the heavier the star, the more massive its core. If the luminary's mass exceeds the Sun's by 8 or more times, its core can overcome the so-called Chandrasekhar limit, which is approximately 1.4 solar masses. In this case, internal electromagnetic repulsion is no longer enough to compensate for gravitational compression. Within a few seconds, the core rapidly shrinks in size, pulling the outer shells with it. The most powerful compression generates pressure so great that even dense matter cannot hold the most elusive particle in the universe. Neutrinos leave the collapsing star, taking thermal energy with them. As a result, the luminary begins to feel insane internal pressure. Tightly pressed protons start to repel with huge force, so the core begins to expand as fast as it compressed seconds earlier, creating a powerful shock wave in the surrounding matter. In the end, an explosion of incredible force occurs, capable of throwing the star's outer shells to a vast distance. In its flame, reactions become possible that can be reproduced nowhere else. This is how heavy elements such as gold, lead, or uranium are born. The formed nebula gradually cools and breaks into separate clouds, which again compress under gravity and turn into new stars and planets. And in place of the dead luminary, a tiny but extremely dense object remains, which is considered a neutron star. If the initial star's mass exceeded 18 to 25 solar masses, its core after the explosion will compress into a black hole, a mysterious object that warps space and time itself around it. Mathematical modeling shows that especially massive stars, whose mass exceeds 100 solar masses, can hypothetically be completely destroyed by the explosion. In such a case, all their matter will be scattered by the shock wave many light years around or converted into powerful electromagnetic radiation. The electromagnetic pulse accompanying a supernova explosion is capable of traveling hundreds of light years. At first, the radiation is characterized by incredible power and is capable of destroying all life in its path. However, as the distance increases, the flux density decreases, and the deadly rays gradually dissipate in space. Calculations show that a star like Betelgeuse could pose a threat within a radius of up to 100 light-years. It is impossible to predict in advance when this luminary will explode as a supernova. However, most likely, it will happen within the next 100,000 years. According to calculations, the flare of Betelgeuse will for a time make the dying star the dominant object of Earth's night sky, and then it will gradually fade. The object will no longer be visible to the naked eye. Only the most powerful telescopes will be able to record the radiation of a tiny neutron star. If Betelgeuse's mass is actually greater than commonly believed, a black hole may form after its explosion. In such a case, the energy burst will be much smaller and the phenomenon much less spectacular. In any case, nothing threatens Earth. Betelgeuse and the gamma burst accompanying a supernova explosion will not be able to harm us. Matter ejected by the explosion will reach the outskirts of our solar system only in 6 million years. According to calculations, its speed will be about 13 kilometers per second and will be easily stopped by the solar wind, never reaching the inner parts of the system. 650 light-years from Earth lies a majestic luminary called CW Leonis, also known as IRC plus 10,216. It's because of this, the core heats up again and the reaction flares up with new force. Receiving a new portion of thermal energy, the stellar shell expands again, stopping the burning. It is believed that this cyclic process is the cause of periodic changes in the star's brightness with a period of 649 days. At the moment of maximum luminosity, the object shines 11,300 times brighter than the Sun. At the lowest point of the cycle, its luminosity is 6,250 times greater than the Sun's. During compression, the upper layers of stellar matter partially tear away from the luminary's surface and replenish the surrounding carbon-oxygen gas nebula that envelopes the giant. According to calculations, this process causes CW Leonis to lose about $4 times 10 carat $14 tons of matter annually. This is approximately 7 times the mass of Earth. Observations show that the age of the stellar nebula is at least 8,000 years. Its mass is about 1.5 solar masses, and its size reaches 84,000 astronomical units. It has a complex structure including clumps, gas clusters, double and uneven rings. It is believed the reason for this is magnetic activity and stellar wind created by the unstable nearby luminary. The chemical composition of the clouds surrounding CW Leonis causes huge interest among researchers. Spectral analysis data show that the circumstellar nebula contains about 70 different chemical compounds, including carbon dioxide, water, and ammonia. Furthermore, the nebula contains many elements from the upper part of the periodic table up to iron. It is quite likely that in the past, planets existed around CW Leonis. However, judging by everything, they were swallowed by the star during its expansion. At least, many years of observations have not revealed obvious traces of their existence. However, in 1994, barely noticeable distortions of the star's orbit were recorded. In 2017, mysterious shifts of matter in the gas-dust environment surrounding the luminary were discovered. Their possible cause could be a small red dwarf orbiting the giant. However, its radiation has not yet been recorded. This might be explained by the nearby nebula scattering or re-emitting the energy flux from nearby light sources. Such a phenomenon masks any objects nearby, not allowing them to be properly examined. It is assumed the mass of the hypothetical stellar companion of CW Leonis is significantly smaller than solar, and it spends approximately 100 years for a full orbit around the giant. Another interesting fact is the relatively high concentration of water in the star's vicinity and shell. It was initially believed that during expansion, the star heated to a temperature of 1,000 Kelvin, which is possible only if water vapor forms directly in the giant's outer layers. This fact did not fit the generally accepted model of red giant structure at the time. According to it, all oxygen in the stellar environment should have been completely spent on forming carbon monoxide. To explain this phenomenon, a new hypothesis was put forward, according to which molecules of silicon and carbon oxides are destroyed by powerful ultraviolet radiation. After this, released oxygen reacts with hydrogen, forming scorched water vapor. The weak point of this hypothesis remains the question of the source of ultraviolet. Such Stephenson 2 to 18 can reach 1.5 billion kilometers, which is 10 times the distance from Earth to the Sun and equals 2,150 solar radii. This means that by volume, this hypergiant exceeds the Sun by approximately 10 billion times. If it were placed in the center of the solar system, Stephenson 2 to 18 would swallow even Saturn along with its rings, not to mention the inner planets. To fly around this giant star along the equator, light would need almost 8 hours. For comparison, in that same time, light from the Sun reaches Pluto at the farthest point of its orbit. The luminosity of this giant, according to calculations, can reach 440,000 solar luminosities. However, its surface temperature is not that high, about 3,200 Kelvin, which is almost twice less than the Sun's. This temperature corresponds to the red part of the spectrum. Therefore, Stephenson 2 to 18 is classified as a red supergiant. Furthermore, such a low temperature means that most of the star's radiation falls into the visible and infrared parts of the spectrum, while the share of harmful ultraviolet and X-ray radiation is insignificant. Despite its giant size and huge luminosity, Stephenson 2 to 18 is not visible from Earth with the naked eye. This is due both to the low temperature of its surface and the clouds of cosmic dust and gas that hide the star from terrestrial observers. They absorb and scatter the light coming from the star, complicating its study. It is not yet known exactly how the internal structure of this star is arranged, but if we assume it is similar to other supergiants, then the mass of Stephenson 2 to 18 should not exceed 20 solar masses. In such a case, the average density of these hypergiants will be incredibly low, approximately at the level of the density of Earth's atmosphere at an altitude of about 90 kilometers above sea level, i.e., almost at the edge of space. Even under such conditions, thermonuclear reactions are maintained in the star's depths, allowing it to shine. The sizes of supergiants are so large that these stars are on the edge of stability. Most of them exhibit variability in their glow, and this variability is, as a rule, unpredictable. This is no surprise, as the absolute majority of such stars are at the final stage of their life cycle and could explode at literally any moment. According to modern ideas about stellar evolution, red hypergiants are stars with an initial mass of 10 to 40 solar masses. The thermonuclear reaction quickly burns hydrogen into helium, after which fusion reactions of helium, carbon, oxygen, and lithium become the source of energy. The lifespan of stars of this type is short, only a few million years. The hypergiant is the final stage of their evolution. In the process of development, such stars rapidly expand and lose mass through powerful stellar winds. Clouds of dust and gas that surrounded the original star are quickly swallowed by the bloated giant. However, its own stellar wind forms a new nebula around the new luminary. Yet, the star's lifetime is insufficient for planets to form in this nebula. Eventually, the hypergiant explodes, forming a supernova or even a hypernova flare. Its outer shells scatter and gradually cool, turning into a nebula, and the core becomes a neutron star or a black hole, depending on the mass. A hypernova explosion is accompanied by a powerful burst of hard X-ray radiation capable of destroying any life within a distance of several light years. Fortunately for Earth, all hypergiants discovered by humanity are much further away. Due to active radiation of charged particles, they gradually lose rotation, and eventually, the outer shells almost completely stop. At the same time, the star's core continues to rotate, and the difference between the core's and the shell's rotation speed can be very large. Thanks to high luminosity, low temperature, and giant size, Stephenson 2 to 18 should possess at least a giant habitable zone at a distance of approximately